So, today we did a revision on the idea of scalars and vectors. And basically the idea behind the two is that both of them have a magnitude and a unit. Magnitude and a unit. The only difference is that vectors have a direction. Right. Now, quick examples of scalars would be things like distance, time, mass, speed. All of them can be quantified, given a number and given a unit, but they do not have a direction. Examples of vectors would be essentially your displacement, and you have velocity and force. Okay, so all of these have a direction, all of these do not. Okay, now revision of that over. Let's have a look at how we can represent them. Okay, but when I say them, I'm talking about vectors. Right, we use vectors representation through an arrow, because an arrow shows direction and the length tells us magnitude. Okay, and how do we find the unit? Well, we give it the unit. So if it's a 5 Newton force, there's a unit. Okay, now ideally we have two different ways of solving for them. We have a scale method and we have the algebraic method. Now let's say somebody went 5 kilometers east and then moved 3 kilometers west. We could do it by scale, saying that 1 kilometer is equal to 1 or proportional to 1 centimeter. So we draw a line that is 5 centimeters long going east and 3 centimeters long going west. And the difference being 2 centimeters according to our calculations could be measured off. An algebraic method is saying that our final displacement would be equal to the first displacement plus the second displacement. The first displacement being plus 5 plus our minus 3. Right. Plus 5 minus 3 gives us plus 2 kilometers. Plus telling us it's east. So therefore we have 2 kilometers east. Right. That's how we can recap and represent vectors. Now, another way to represent or look at these diagrams is through a force diagram. Force diagram and free body diagrams. Okay, now free body diagrams and force diagrams are slightly different. The main difference, if we have an object on a plane, so if it's just sitting still, we have the force of gravity and we have the normal force. Force of gravity always comes from the center of gravity, normal force from the surface. Those are coming from different points, different objects. A free body diagram composes them into from a single point, where we have the normal force and the force of gravity acting on a single point. Alright, now we can take this type of thing into multiple different types of forces, and especially if we start looking at objects which have an unequal force acting on them. let's say this is a smooth surface and it is being pulled to the left and right by an applied force, it still has a force of gravity and it still has a normal force. Thus, we end up getting a free body diagram looking like that. Alright, now let's say there's a rough surface with no movement, and we end up getting an object on the plane with an applied force, obviously with a force of gravity, normal force. The force of friction acts in the opposite direction to the applied force. So if it's being pulled, it means that the force of friction is going to be acting in the opposite direction. So, force of friction. If it's no movement, it means all forces are equal. That means our force, or normal force, is equal to the force of gravity. Our force that is applied is equal to the force of friction. Alright, so that is basically free body diagrams. Next, we're going to have a look at other diagrams on a slope and with angles.